Thank you very much, Rodrigo. So first, I would like to thank the AMS and Georgia, Elling, and Rodrigo for giving me the opportunity to give the talk today. So the purpose of the talk will be to introduce some ideas which are related to sets of finite perimeter and associated theory of bounded variation functions. So this is a theory I've actually been interested in relatively recently. That goes back to 2017, and my interest came from attending a series of beautiful lectures by Nagesh Shanmuganingam in Levico Summer School. So I would like to describe the viewpoint which is related to the connection between heat kernel techniques and the theory of the sets of finite perimeter. So the theory of sets of finite perimeter is closely related to the study of isoperimetric inequality, which have a very long history in the history of mathematics and beyond, and goes back at least to the legend of the Queen Dido, who was, according to Greek and Roman sources, the founder and the first queen of Carthage, Carthage being an ancient city in modern-day Tunisia. And the legend says that when Queen Dido arrived on the coast of Tunisia, she asked for a piece of land. So the request was satisfied by the local king, provided that the land could be delimited by an ox hide. So the legend says then that this land became Carthage and Dido became the queen. But the question is, what is the shape of the land chosen by Queen Dido? That is, we can rephrase this problem a little bit more mathematically. The problem faced by Queen Dido was the following. Given a curve of given length, that I'm going to call the perimeter of the curves for now, that is given a curve of given length P, what is the shape for which the area enclosed by this curve is maximal? So here, for the sake of simplification, we just understand the perimeter as being the length of the curve, and the curve we are considering is supposed to be smooth enough so that the length is well defined. So this is what we call the isoperimetric problem. As is intuitively clear, the solution to the isoperimetric problem should be a circle. And therefore, the shape that maximizes area for a given perimeter P is going to be the disk. There is a clean and elegant way to represent the solution of the isoperimetric problem, which is the isoperimetric inequality that provides a quantitative solution to the isoperimetric problem. More precisely, for nice sets, the area of the sets can be bounded from above by a constant 1 over 4 pi times the perimeter square of the set. And this equality is achieved in the case where the shape, that is the domain in the plane, is a disk. So this is what we call the isoperimetric inequality. So as a consequence, and we can still see that today, the city limits of Carthage formed a half circle, and we can still visit nowadays the ruin of Carthage. If you visit Tunis in Tunisia, you can still see the ruins, and a small museum there explains, the story of the Queen Dido and the relation with the isoperimetric problem in the plane. So of course, as mathematicians, we like to formulate problems at different levels of generality and in a form that can be generalized to different settings. So for the isoperimetric problem, if we want to state it in Rn, one needs fundamentally two notions. The first notion is a notion of a volume of a set, and the second notion is the notion of perimeter. So these two fundamental notions have been at the source of most of the spectacular development in geometric measure theory, and was developed throughout the 20th and the beginning of the 21st century. So the notion of volume was formalized relatively quickly and is based on seminal work by Henri Lebesgue in 1901 and 1902. More generally, one can understand volumes in the category of measure spaces. So in particular, the volume of a set in Rn is understood at its Lebesgue measure. The notion of perimeter is more elusive and took much more time for mathematicians to formalize rigorously. So actually, the notion of perimeter can be understood from different viewpoints, yielding different generalizations. So one of the first basic definition is due to the Italian mathematician Renato Caccioppoli, who proposed in 1927, 1928, a first approach to the notion of a perimeter of a set in Rn. So he did his approach when he was only 23, 24. And this is the intuitive notion of what should the perimeter of a set represent. That is, the definition is similar to the definition of the length of a curve that was proposed a few years earlier by Giuseppe Peano. And the idea is to approximate sets in Rn by sets for which the notion of perimeter is straightforward, or at least intuitive. And he shows approximations of sets in Rn by polyhedra, defining the perimeter of a polyhedra as being the sum of the areas of the faces of the polyhedra. So the idea will be that we approximate a set in Rn by a family of polyhedra. We let the family of polyhedra converge in some sense to the original set, and we look at the limit of the sum of the areas of the polyhedra. So this notion of perimeter is what really a perimeter should represent. However, it's very difficult to use concretely this definition in analysis and for concrete computations. So 30 years later, Caccioppoli came back on his original definition and formulated an equivalent definition, actually, of sets of finite perimeter, which is in some sense due all to the first definition. So the idea is to define the perimeter of a set using the Gauss-Green formula. And this is quickly realized using heuristic based on the Gauss-Green formula, that the perimeter of a set, as defined 30 years before that, should also be the supremum of a functional, which is an integral over the set of the divergence of the vector fields for which the norm of the vector fields is less than 1. So this definition is much more flexible to use for mathematicians and is easy to generalize to different settings. So in a weak sense, that is what is the intuition given by this variational characterization of a perimeter of a set, is that one can understand, at least in some weak sense, the perimeter of a set as being the integral over Rn of the norm of the gradient of the indicator function. So the idea is that the gradient of the indicator function of the set should look like a Dirac distribution, which is supported on the boundary of the set. That is, this is where the gradient is not zero. So this intuition of a perimeter of a set as the integral over Rn of the norm of the gradient of the indicator function is an intuition that is going to motivate most of the development in the theory of sets of finite perimeters that I'm going to present in the next few slides. So now that the notion of volumes and perimeters are well defined in Rn, using the volume from Lebesgue theory and the perimeter from Caccioppoli theory, one can state rigorously the isoperimetric in Rn that generalize the isoperimetric inequality that Quid-Nido solved when she founded Carthage. So the problem mathematically is the following. Among measurable sets of given perimeter, what are the sets of maximal volume? Again, in the Euclidean case, it should be relatively intuitive that the sets are both. That is, for symmetry reasons, the sets maximizing the volume for a given perimeter should be the both. And we have, as we did in the case of the plane, a corresponding isoperimetric inequality that quantifies the solution of the isomeric problem. So namely, it's possible to bound from above the volume of a set to some power, which is n minus 1 over n, by a constant times the perimeter of the set. And the equality, this is inequality, is achieved for both. This is the isoperimetric inequality in Rn using the notion of volume given by Lebesgue and the notion of perimeter given by Caccioppoli. So a convenient way to study this set of finite perimeter is to introduce the theory of bounded variation functions. So in a sense, bounded variation functions are to set of finite perimeter what the L1 functions are to set of finite measures. That is, one can parallel the construction of BV functions from the notion of sets of finite perimeter with the construction of L1 once a notion of sets of finite measure is well defined. So the functional characterization given by Caccioppoli defines almost in a straightforward way a notion of BV function. And the intuition is the following. In the weak sense given by Caccioppoli definition, a function is going to be of bounded variation in Rn if the integral of the norm of its gradient, again in a weak sense, because typically we don't assume that the BV function we consider are smooth. So you should understand the gradient in a weak sense given by Caccioppoli. So if this gradient is in L1, this is what we call a bounded variation function. So dealing with functional spaces of bounded variation functions will allow a lot of calculus that we can then use to study sets of finite perimeter. So in that setting, obviously, a set is going to be a finite perimeter in Rn if and only if its indicator function is a bounded variation function. So then there is an equivalent way to express the isoperimetric inequality, which is a geometric inequality, into a functional form. That is, it has been realized in the early 60s after work by Mazia, Federer, and Fleming, that the isoperimetric inequality in Rn is actually equivalent to a functional inequality on the BV space. More precisely, there is an embedding of the BV space into LP space, where the exponent p is given by n over n minus 1, which is exactly the exponent that appeared in the isoperimetric inequality. And the constant in this functional inequality is exactly the same as in the isoperimetric problem. So it turns out that the L1 Sobolev inequality, that is, this is the name of this functional inequality, is equivalent to the isoperimetric inequality in Rn. So this is easy to see that the L1 Sobolev inequality implies the isoperimetric inequality. Indeed, if you just plug in f to be the indicator function of a set with finite perimeter, we recover immediately the isoperimetric inequality in Rn. But it turns out that this is also possible to prove the L1 Sobolev inequality from the isoperimetric inequality. That is, this functional inequality is equivalent to a geometric inequality, which is the isoperimetric inequality. So there exist dozens of proofs, of the L1 Sobolev inequality, or equivalently of the isoperimetric inequality in Rn. So there exists a proof by rearrangement inequality, which is a proof by Gagliardo and Nirenberg. There exists proof by Fourier transforms technique using the Ritz kernels. There exists proof from convex analysis that rely on Brun-Minkowski inequality. There exists PD proof, there exists optimal transport proof, there exists probability proof. So there exists really plenty of proofs. And interestingly, this proof generalized in different settings. So this is always interesting to know as many proofs as you can for a result you like, because each of the proofs will show you a phenomenon of the result you're interested in that will generalize in different settings, in different directions. So there is a proof I liked a lot personally, which is a heat kernel proof for the isoperimetric inequality, or equivalently for the L1 Sobolev inequality. So this proof took some time to be developed in full generality, and goes back to preliminary works by Varopoulos that were then further developed by, among others, Ledoux and Salovkost. And an interest of this proof is that it uses very little structure of the underlying space. That is, the proof was originally developed in the Euclidean space Rn, but the specificity of the Euclidean structure does not play a role in the approach by Varopoulos, Ledoux, and Salovkost. So this approach can be applied as it is to a much larger class of spaces, including the metric spaces I'm going to mention in a few minutes. So some comments about the heat flow approach to isoperimetry and L1 Sobolev inequality. It is that since the origin, actually, of the theory of sets of finite perimeter, it has been very quickly realized that the theory of sets of finite perimeter is very closely and intimately related to the heat kernel and to parabolic differential equations. That is very soon, or almost at the same time, when Caccioppoli proposed his definition of sets of finite perimeter, De Giorgi developed the first characterization using heat kernels of the sets of finite perimeter. So precisely, it's possible to characterize completely BV functions only in terms of the heat kernel, and a function f is going to be a bounded variation function if and only if the lim sup, which is written in the slide, is going to be finite. So this is a heat kernel characterization of the space of bounded variation functions. That is, this is an if and only if. And this heat kernel characterization of the BV space allows to import all the techniques from heat equations and from heat kernels to the study of the space of BV functions. So this is for the good news about the heat kernel approach, is that the heat kernel approach to isoperimetric inequality is very general and is going to work in a very large class of spaces. However, of course, the price to pay is that we lose the optimal constant applying heat kernel technique. That is, the approach is going to be very general, however, does not yield the extremos in the isoperimetric inequality. That is, it only yields an inequality that relates the volume of a set to its perimeter but does not tell you what are the extremals in this inequality. So in this approach, the study of extremals is a separate problem. And it's actually a very difficult problem, which is still open, even in very simple situations, like the three-dimensional Heisenberg group. That is, the heat kernel approach provides an isoperimetric inequality. That is, we know that there exists an isoperimetric inequality, but in many examples, we don't know what are going to be the extremals in this isoperimetric inequality. And this is given by a separate theory. So a basic motivating question, once we understand sets of finite perimeter and corresponding set of BV functions in the Euclidean set, in the Euclidean space, will be to see how far can we push those ideas in a more abstract setting, in particular assuming that we are interested in spaces which are not vector spaces or which are not even manifolds. So I will present first the case of metric measure spaces, for which the study of sets of finite perimeter and BV function attracted a lot of attentions. So consider an abstract metric measure space, meaning that you have a space X that can be very rough. So it could be a fractal, it could be a manifold, or it could be your favorite space, on which you have a metric, that is, you have a way to compute the distance between 2 points on that space. And you have a measure, that is, you have a way to compute volume of sets. Given only the measure, that is, given only the geometric notion of volume and the geometric notion of distance, can you define what is a set of finite perimeter? This is not an obvious question, right? Because if you go back to the original definitions by Cacciopoli, both of the characterization by Cacciopoli uses some additional structure of the space. That is the first definition based on generalizing the notion of rectifiability uses polyhedra, which are very specific to Euclidean spaces. And the second definition using Gauss-Green formula, that is differential calculus. So this definition holds in the context of Riemannian manifolds or even sub-Riemannian manifolds, but will be very tough to define in metric spaces for which you do not have differential calculus. Okay, so this is a basic motivating question, geometric question. Can we understand the perimeter of a set? Can we define it in a meaningful way using only volume and distance? So equivalently, can we define BV functions, that is bounded variation functions, in this abstract setting? Then, of course, we would like that our definitions of BV functions and sets of finite perimeter generalize in a nice and elegant way what we know in the Euclidean space. So in particular, can we prove meaningful isoperimetric inequality in spaces which are possibly very rough? So in the context of metric measure spaces, we can start with an almost naive idea, that is, in an abstract space, that is where we have only volume and distance, we don't have a gradient. But let's think about what could replace, the integral of the norm of the gradient in a metric setting. So the idea would be to use a metric approximation of a gradient that may not be defined pointwise, a metric approximation which is based by an integral over a ball whose radius goes to 0 when we approximate the gradient by the ratio of the function, that is the increment of the function, over a ball whose radius goes to 0. And we take the limit when r goes to 0. So this is an almost naive idea to replace the gradient by a metric approximation. However, we are going to see that this idea is going to be fruitful enough to develop a theory which is reasonable and intuitively correct, at least in some large classes of metric measure spaces. So a few comments is that in smooth cases like Euclidean space or maybe manifolds, the parameter lambda, which is used in the metric approximation of the gradient, should be equal to 1, because the idea is that in a large class of metric spaces which are smooth, a smooth function in that metric space should be locally Lipschitz. That is, if we want a limit to be meaningful for the fy minus fx over r to the power lambda, we take lambda is equal to 1, because in our mind, smooth functions are locally Lipschitz on regular metric spaces. However, this intuition is not correct anymore in other type of metric spaces like fractals, because in that setting, we should think of smooth functions as not being in the Lipschitz category anymore, but they are rather in the Hölder category. That is, in the framework of fractals, like the Sierpizzi gasket, or the Sierpizzi carpet, or the Wilczek set that we are going to see quickly in a moment, we should think of smooth functions as not being Lipschitz functions. So in that case, the parameter lambda that we choose for the metric approximation of the gradient will not be equal to 1. So this naive idea can be formalized introducing a scale of spaces, which is well defined on general metric measure spaces, which have been called the co-reversion spaces, and which are a family of spaces defined using this double integral, which is called the L1 co-reversion energy of the function. And this family of space depend on the parameter lambda that intuitively is going to quantify the regularity of the function. That is, to develop a theory of smooth functions in a possibly very rough space, we want to take lambda as large as possible. So in this L1 setting, the functions which are going to be the most regular one using the L1 co-reversion energy should be the BV function. So we introduce a critical parameter in this scale of spaces that quantifies the regularity of functions as being the supremum of the parameters for which the scale of space contains non-constant functions. That is, these are the most regular functions in this family of L1 type spaces. And the BV space we are going to be interested in and study will be this co-reversion space, that is this space of functions, which is defined as the critical exponent. So of course, once we implement this idea and this intuition, we would like a reality check, that is a sanity check, to make sure that the definition we work with are meaningful in the example that we like for instance, Rn, or maybe possibly manifolds, and even metric spaces for which we have a lot of structures. So it turns out that in the case of the Euclidean space, this approach, to the space of BV function coincides completely with the Caccioppoli approach. That is, the definition of the space of BV function is the same. And we don't lose anything using the co-reversion approach or using the Caccioppoli approach. That is, the critical exponent in that case is equal to 1, and the theory is the same. And more generally, it has been proved in 2016 that the theory of co-reversion, that is the co-reversion approach using a metric approximation of the gradient, is the same as a theory that some people have been developing since the early 2000s in the context of metric measure spaces, which are relatively regular in the sense that they admit what we call an upper gradient structure. So I'm not going to enter too much into the details here. So metric spaces with upper gradient structures are metric spaces for which there are a lot of rectifiable curves, and for which Lipschitz functions are smooth functions. So in this class of spaces that satisfy some regularity, like doubling property or one Poincare inequality, the theory of BV function given by the correlation approach would be the same as the theory of BV function based on upper gradient that was developed by Miranda in the early 2000s. So in these two classes of spaces, that is Rn manifolds or metric measure spaces, which are relatively regular, we don't lose anything if we use the correlation definition of BV to work with BV functions. But there are some advantages of the correlation approach, that is to use these naive ideas that we had at the beginning, is that first, this is intuitive. Of course, that is, if we think that the variation of BV function should be the L1 norm of the gradient, we use a metric approximation, of the gradient, and we look at the integral of this metric approximation. This is something which is very intuitive. This is well defined, and meaningful in all metric measure spaces. That is, you can study, if you want, the scale of spaces given by the correlation energy in any metric measure space. And this is the aspect for which I was fascinated by the theory. This is a close connection between this approach of correlation and the theory of Dirichlet forms, which is an object that was introduced in the 1950s by probabilists and people in potential theory. That is, the correlation approach to BV functions is very closely related to the prolific theory of Dirichlet form. And I'm going to show you some of the connection and some of the ideas that we can use to study BV functions and therefore sets of finite perimeter using the theory of Dirichlet form, which is an L2 theory. So maybe there are questions at that point? Or?
There are no questions posted right now.
Okay, thank you, Rodrigo. So Dirichlet forms entered into the play in the middle of the 20th century, and they were formally introduced in a long and very nice paper by Burling and Dunny in 1958 and 1959 to develop a potential theory in abstract measure spaces. That is the goal of the Dirichlet forms, were to study capacities of sets in the general context of measure spaces. That is, the goal was to define capacities in abstract measure spaces. So very roughly speaking, Dirichlet forms gives a meaning, that is, they define the integral of the square of the norm of the gradient in a very weak sense. So this is an energy form that can be introduced and defined in very general spaces. So the theory of Dirichlet forms, since its introduction, attracted a lot of attention and is now a centerpiece, in a lot of modern mathematics, because Dirichlet forms turns out to be a tool which is at the intersection of many different fields. So this is a tool which is used in PDE. This is the tools that appear in functional analysis, and this is actually the origin of the theory of Dirichlet forms. Tools that can be used in metric geometry, and also which is closely connected to probability theory. So actually Dirichlet forms have been studied by probabilists for more than 30 years now, due to their very close connection with the theory of Markov processes. So as such, since Dirichlet forms lie at the intersection of different areas, they can be used to make bridges between seemingly different fields. Like, for instance, the fields I'm going to discuss today, which is the fields of BV functions, which takes its root in geometric measure theory, but that can be understood using tools from probability theory, for instance. So I would like to give at least an intuition of what is a Dirichlet form. So I told you that a Dirichlet form is a way, is a tool to give a sense to what is the integral of the square of the norm of the gradient in a very abstract spaces. The advantage of dealing with the functional, the integral of the square of the norm of the gradient is that we have the very rich theory of Hilbert spaces to give a very weak sense to what we mean by an energy form, like the integral of the square of the norm of the gradient. So more precisely speaking, a Dirichlet form on a metric measure space, x d mu, is a bilinear form on the Hilbert space L2 that can be written as an integral of some energy form, of some energy measures that are going to satisfy Leibniz rule. That is, this is important, it's in general definition that we don't assume the energy measures, that is defining the Dirichlet form, to be absolutely continuous or equivalent with respect to the reference measure mu. That is, in situations like fractals, we are going to be interested in a little while, the energy measures we are going to consider are not equivalent or not even absolutely continuous with respect to the reference measure. So for a manifold, for instance, the canonical Dirichlet form is given in terms of the Riemannian, structure and the Riemannian gradient. But in general, the Dirichlet form we'll be interested in are not comparable to the reference measure. So some tools that is associated with the theory of Dirichlet forms, that is, they come with a toolkit belonging to either functional analysis, like Laplacian, which is defined using a weak form of integration by parts. Given a Dirichlet form, it's possible to define a Laplacian, which is going to be defined on a dense domain of L2 using integration by parts, and to define a corresponding semigroup generated by the Laplacian. That is, Dirichlet forms allow to construct a Laplace operator on the space and a corresponding Hit semigroup. Then there is a probabilistic interpretation of what is a Dirichlet form. Equivalently, a Dirichlet form is a family of continuous Markov process on the space. That is, there is an equivalence between the theory of Dirichlet forms and the theory of continuous Markov processes. And finally, there is another tool that comes from analysis this time. This is PD, and it turns out that Dirichlet forms and associated semigroups are related to the Hit equation. That is, it's possible in many situations to introduce a fundamental solution of the Hit equation on the space, which is associated with the Laplacian, and to study analytically the solution of this parabolic partial differential equation to get information about the Dirichlet form. So from the very beginning of the theory, we see that Dirichlet forms comes with tools from different areas, functional analysis, probability, or partial differential equations. So what is the connection between Dirichlet form and BV class? So Dirichlet form is a weak sense to the square of the norm of the gradient. BV class is a weak sense of the integral of the norm of the gradient. So intuitively, we would like to take some square root to go from one space to the other one when we can. But this is not something, of course, that we can make rigorous, because it's not possible to take square roots of measure in general. So I want to illustrate the deep connection between BV function and Dirichlet forms in two settings. The first setting will be the setting of regular metric spaces, which for specialists are going to be spaces with upper gradient structure. And the second setting will be the class of spaces of fractal-like spaces, which are spaces for which there is no upper gradient structure. So the main difference between these two classes of spaces is that the relevant Dirichlet form in the first setting are going to have energy measures which are absolutely continuous with respect to the reference measure. So we'll be able to take square roots. In the second setting, it's not possible anymore, because it turns out that the energy measures for the canonical Dirichlet form are singular with respect to the reference measure. So the first setting is the setting of metric measure spaces that are not too far from manifolds. That is, these are metric spaces for which there are a lot of rectifiable curves connecting 2 points. So if you are not very familiar with the general framework of metric measure spaces, you could think of Riemannian manifolds, or you could think of limits of Riemannian manifolds with non-negative Ricci curvatures. Or a little bit more generally, if you are familiar with this, you could think of RCD spaces. This part also covers, for instance, the case of Carnot groups, or even more general sub-Riemannian manifolds, or also applies to metric graph. So in that case, the connection between the BV functions and the theory of Dirichlet forms was uncovered in 2016 at this paper by Miranda, Marola, and Shannon Gallingham, where implicitly they prove that there exists a Dirichlet form on this type of spaces, which turns out to be equivalent to the L2 correversion energy. That is, the L2 correversion energy is defined in terms of a lim sup. So this is not clear at all that it's going to be equivalent to a Dirichlet form when R goes to 0. But it turns out that using the metric approximation for the square of the norm of the gradient yields actually a Dirichlet form at the infinitesimal level. So this is a connection between the correversion approach, metric gradient approach, and the theory of Dirichlet form, is that infinitesimally there exists a Dirichlet form which is going to control the L2 energy we are interested in at the beginning. So Dirichlet form, once we have the existence of such Dirichlet forms that exist infinitesimally, we have all the tools associated with the Dirichlet form, and in particular, we have heat kernels. So heat kernels, they come with a lot of techniques. In particular, probabilists know very well how to estimate heat kernels, that is to give upper bound and lower bound for the heat kernel, and how to compare heat kernel on very general spaces with the Euclidean one. And in this context of regular metric spaces, it can be proved that the heat kernel on the space, that is the heat kernel associated with the Dirichlet form, which is equivalent to the L2 correversion energy, has a Gaussian size. So then, using this heat kernel, we can then characterize the BV space as what done in the Euclidean space. So it was the origin of a work by several authors, by Patricia Alonso-Ruiz, by myself, by Li Chen, Luc Rogers, Nagesh Gallingham, and Sasha Teplayev, to realize that in a large class of spaces, the BV space, defined by the correversion approach, is the same as the BV space using a heat kernel characterization. That is, we can characterize BV functions in this class of metric spaces using heat kernel. And this is exactly the same characterization as we had in the Euclidean space. So with the heat kernel tools in hands, well, it's possible, to apply all the ideas that have been developed around heat kernel, and in particular the so-called Bakry-Ledoux calculus of heat semigroups to study the BV space. So once we have the heat kernel, we will have a lot of techniques to study the space. So in particular, Sobolev inequality and the corresponding isoperimetric inequality can be deduced in this large class of metric measure spaces using the Dirichlet form associated with the L2 correversion energy, and using heat kernel techniques which are valid in very general spaces. So it's interesting that in that setting, the isoperimetric inequality we get is exactly equivalent, and recovers and generalizes the isoperimetric inequality of the Euclidean space. And as a variation of a function, we can use a lim-inf. That is, we can use the optimal quantity, associated with L1 correversion energy. So this is a natural extension of the isoperimetric inequality in a large classes of metric measure spaces. So a second class of spaces in which I would like to introduce the method, that is, how do we study BV space and sets of finite perimeter using Dirichlet forms and heat kernels. This is a setting of fractals. So this setting of fractal is interesting because, as I told you before, the intuition is that smooth functions are not Lipschitz anymore. They are only Hölder, continuous. So the calculus with Lipschitz function that you use, in regular metric spaces is not going to work in the fractal framework. So the loose definition, the rough definition of a fractal I'm going to use in this talk is a definition of a nested fractal, which is a set embedded in the Euclidean space Rd, which is going to be let invariant by a finite family of contractions. That is, you consider similitudes, psi1, psi2 up to psi-m, a finite family of them, and you study a compact set which are invariant by this finite family of contractions. Such compact set is called a nested fractal. So there exist two famous examples. So maybe the most famous one is the Sierpinski triangle that already appeared in yesterday beautiful talk by Malabika. So it seems that the Sierpinski gasket is popular in this conference, and it can be constructed very simply by starting with 3 points, forming the vertices of an equilateral triangle. So you start from the 3 vertices, and you consider 3 similitudes with the contraction factor 1/2 that are going to act on these 3 points. That is, you iterate the 3 vertices using this family of similitudes, and you get a unique set, which is like stable, invariant, by this family, which is the so-called Sierpinski gasket, which looks like this beautiful picture which is on the slide. Another beautiful example that I like a lot is the example of the Vic-Sheck cross, or the Vic-Sheck set, which is obtained by iterating a family of 5 similitudes starting from 5 points. That is, you start from a unit square, for instance. You consider the vertices of the square and the center. So this is a beginning family of points. And starting from this family of points, you iterate a system, a chaotic system of similitudes, which is given with a factor 1/3. And you get this beautiful picture of the Vic-Sheck cross at the bottom of the page. So these are examples of compact nested fractals. That is, nested fractals intuitively are sets embedded in Rn, which are stable, invariant by a finite family of similitudes. But very often, for analysis, we like not to be bothered by boundary condition. So we like to work in infinite spaces. So in particular, to speak about isoperimetric inequalities, we like to work in an unbounded space. So to do this, we can consider what we call the blow-up of the fractal, which is just defined by using dilations, of the regional fractal by all possible factors L to the n. So this is the corresponding unbounded fractal. So then fractal, that is this type of spaces, are metric measure spaces, right? That is, a fractal X is a set which is embedded in Euclidean space Rd, and therefore it comes with a metric, which is a restriction of the Euclidean metric. There is also an intrinsic measure, which is going to be associated with a fractal, which is a Hausdorff measure. So if we have a metric and a measure, we therefore have a notion of BV space in the sense of correvariation. So we can study the scale of spaces using the metric gradient approximation in that family of spaces. And it turns out that this parameter lambda that was equal to 1 in regular metric spaces, in the fractal case is not equal to 1 anymore, reflecting the fact that smooth functions, they are not locally Lipschitz anymore, but they are locally Hölder. And it's possible to compute explicitly the L1 correlation exponent. It's equal exactly to the Hausdorff dimension of the underlying space. So in this theory, when the critical parameter is not equal to 1, but is strictly more than 1, intuitively it means that the set of finite perimeters that we get using this theory, they will have a codimension which is strictly more than 1. So the parallel with the theory of Dirichlet forms is given by the following result that says that, as was the case in metric regular spaces, it turns out that there exists a Dirichlet form that exists infinitesimally on the fractal, and which is comparable to the L2 correlation energy, the L2 correlation energy being a weak meaning to the integral of the square of the norm of the gradient. So once we have the Dirichlet form that exists, we have therefore the corresponding heat kernel. And let me point out very quickly that the Dirichlet form is relatively explicit in the fractal case and was studied almost at the beginning of the theory of fractal. It can be defined as the limit of energy forms, which are defined on graph approximations. And once we have the heat kernel associated with the Dirichlet form, we can use the same heat kernel techniques as we did, in Rn, or as we just did in the context of metric measure spaces. And in particular, we obtained the heat kernel characterization of the BV space using the heat kernel of this canonical Dirichlet form that lives on the Dirichlet, on the fractals. Okay, so once we have the heat kernel characterization, as I told you, the method is very general. That is, we can obtain, adapting, of course, with a little bit of work, but we can obtain the isoperimetric inequality and the L1 Sobolev inequality in this context of fractals. Again, we are able to use a correlation energy, which is a lim-inf, that is, which is the best possible way to estimate what should be the variation of a function. So this is, and maybe, how long do I have, Rodrigo?
Couple of minutes, just a couple of minutes, Fabrice.
Yes, okay. So I'm just done, I think, in 2 or 3 minutes. So just to conclude, so I focus my attention in this talk on the study of sets of finite perimeter and BV functions, because I like a lot the isoperimetric inequality, which is a geometric inequality. But it's possible also to develop the theory of Sobolev spaces. That is, instead of starting with a metric approximation of the norm of the gradient and its integral, we can use, the same naive idea that we did for Sobolev spaces. That is, it's possible, to use LP correlation energy, that is to use a metric approximation of the integral of the norm of the gradient to the power p to get a theory of Sobolev spaces on abstract metric measure spaces. It turns out that this theory is very rich, and we can recover, the well-known embeddings theorems that hold in Euclidean spaces or in metric on regular metric spaces like manifolds or sub-Riemannian manifolds. That is, we can recover the Gagriardo-Nirenberg inequalities in that framework. We can also prove new LP Poincare inequalities in fractals cases, for instance. And as it should be apparent, and maybe I will finish with that, is that what matters really in my talk and what matters for the method I am using is the heat kernel characterization, right? And heat kernels, they are defined well beyond the context of metric measure spaces. If we have a Dirichlet space, essentially we have a heat kernel, or at least a heat kernel measure. Therefore, using this characterization that was so important in my explicit frameworks, I'll be able to develop a theory of BV spaces in general Dirichlet spaces that is going to generalize the framework that we just studied in the talk. So this can be done, and this is the way we presented the theory, in the series of papers dating back to 2018 to develop the theory of BV function in abstract Dirichlet spaces and show how it generalizes the well-known theory in Rn, Riemannian space, sub-Riemannian spaces, and show how it applies to new situations like fractals. So the idea is to use the heat kernel characterization of BV functions to define the BV space. So thank you very much for your attention. So I think this is all what I wanted to discuss today.
Thank you, Fabrice. Do we have any questions? There is a question here on the chat that says, do you know the optimizers for your isoperimetric inequality?
No, in general, no. That is, it's a very difficult question, actually, which is separate, from the problems I've been discussing in the talk. That is, for instance, in the context of even the three-dimensional Heisenberg group, the question is still open today about what are really the extremals for the isoperimetric inequality. That is, the heat kernel method, that is a very general method I presented today, give you that there exists an isoperimetric inequality, which behave as you should expect intuitively, but it doesn't tell you what are the extremals in this inequality. We need more structure on the space than the structure of a Dirichlet space.
Okay, another question coming from a non-specialist. Can you explain why the Gaussian is appearing in the kernel?
Why the Gaussian is appearing in the kernel? So, for instance, in the Euclidean case, the Gaussian is appearing in the kernel through the Fourier transform. That is, the Gaussian essentially is an eigenvector of the Fourier transform. So if you apply the Fourier transform, to the heat equation, you are looking at eigenvectors of the Fourier transform. And very roughly speaking, eigenvectors are the Gaussian functions. So this is how they appear first in connection with the heat equation. There exist connections, of course, with probabilities that can also be relatively intuitive, but maybe the simplest interpretation is using Fourier transform.
Fabrice, I have one question myself. So in most of these problems, it seems so the semigroup, the heat semigroup has finite dimension in the language of Varopoulos, right?
Yes.
So
yes.
It maps L1 to L infinity with the decay, which is power of T, right?
Yes.
And is this the essential point in all of these in relating it to the BB functions?
Oh, yes, that's a very very interesting question. Actually, the dimension of the semigroup that you mentioned is the one that appears, in the Sobolev embedding. That is the exponent n over n minus 1. The n is exactly the semigroup dimension of the space. So, for instance, to develop the theory of BB functions in infinite dimensional spaces like the Wiener space, instead of using the semigroup dimension, we will have to use hypercontractivity of the semigroup, where isoperimetric inequality, like I presented them, should be understood as a Gaussian isoperimetric inequality in a form which is independent of the dimension. So the theory is still in development, I should say. That is, applying our theory in infinite dimensional spaces is not completely finished yet, but we have hope that we can still recover the theory of BB function in the Wiener space by using this Dirichlet form approach. So far, yes, the dimension plays an important role, at least in what I presented, but we do have some hope to bypass this restriction using hypercontractivity instead of ultracontractivity.
Thank you very much for this very interesting talk and beautiful mathematics. So